well, this is always kind of stable, except for what Surajit was saying, close to zero, but where they kind of flat out. And so they this is more stable, and plus this is more more to the point of what the autoencoder is trying to do. Yes.
One could suggest that you could use cross entropy for something like this pixel-wise, but the reason that doesn't work is because cross entropy isn't a symmetric loss function.
Exactly.
So if you go a little over, it's not the same penalty as if you were a little under for a specific pixel value.
Yes.
Compared to the data.
Yes, which is kind of the same point of the K of the vertex. Yeah. So, to be fair, like I used the autoencoders a few times, but like I'm not probably an expert of like autoencoders and variational autoencoders. I work more with GANs. But yeah, I mean, autoencoders are still useful for, as I was telling you, to do classification tasks. They more often than not avoid some kind of overfitting of the training data, because the features that you find are not specific to the task you're trying to perform, right? Is everybody with me up to now? Okay.
You mean classification, right? Useful for classification, yes.
Yes. Yes, like when you throw away the decoder, right? When you have trained it, you can throw away the decoder and keep the encoder and attach a classifier to the encoder and train only the classifier based on the features that you found during the training of the autoencoder. So, okay. Let's talk about variational autoencoders. There are some little differences between autoencoders and variational autoencoder, but the big difference is that a variational autoencoder is actually a generative model, right? So the point of the generative model is to model the real distribution of the data, so to be able to sample from that distribution, even samples that are not in our training data, right? So, so how do we do this? We are, in this case, we are more interested actually in the decoder than in the encoder. What we do for this, like, let's assume that we have this training data, right? Each xi is one sample from the training data. So we want to learn to sample from this distribution. So, as I was telling you, we already know that this Z space is an embedding, right? So the Z space contains can contain some important characteristics from the data. We can train it from an autoencoder point of view, right? So we already know that we're able to do this. So in this case, we are modeling the probability of the data as like with a decoder. So this p theta star, p theta is the probability distribution enforced by the decoder. Okay, p theta star is basically the encoder that matches precisely the training data. Okay, so if we sample from Z, we should be able to pass it into the decoder and obtain some real data, right? The fact is that we want Z to be some good distribution, some distribution that we can model from scratch, right? That we don't have to learn from the data, some prior. So we often use, for example, a Gaussian distribution, right? We know how to sample from a Gaussian distribution, right? So if we are able to actually have this Gaussian distribution containing some meaningful characteristic of the data, we can sample from there and obtain this distribution from a distribution that we know. Does it make sense? Yes? Any questions?
So, since we have so many training data, could we just use the ZI to make a density estimate for the prior?
Yes. Redefine, like, maybe I didn't understand. Can you tell me again?
So once we have learned the encoder, we also know the ZI for the XI, right? We also know the values ZI.
Yes.
So we just use this ZI to fit a density, to fit a probability density. So to take that as the prior.
I think you should be able to do that, but I have never seen anyone doing this.
So what he's possibly trying to tell is that you're using the autoencoder, you get the embedding in the latent space and you reconstruct. But that is not that easy, because in high-dimension space, construction of the probability density function
is not that easy. That's why you want to have Z more as a known prior rather than a learned posterior, right? Because if you force Z to be a multidimensional, whatever, uniform or Gaussian, you can sample from that and generate. Doing the opposite, you will find values. If you look at what like a normal autoencoder finds, like those features, like they have values that can have very, very wide ranges, that can have like, they could be hard to model directly from there. Even though the space is smaller, trying to find the distribution of those is actually hard. Okay. So, okay. So this is exactly what I just told you. So we want to find this this theta star, right? The parameters of the decoder that will model the distribution of the data in the best way. So how should we represent this model? As I was saying, you choose a prior PZ that you know, which is more often than not a standard distribution. A Gaussian distribution, and we use it to model the latent attributes, the latent space, the embedding I was talking about, right? So since this conditional P of X and ZI is not directly tractable, it's actually easier to do this task through a neural network. So let's talk about training the model, right? So we want to model this probability distribution through the neural network. Now we have defined Z, right? Because it's a prior, we know which one it is because we chose it. This is intractable. So we chose a simple Gaussian. We use a decoder to do that, to model this P of X given Y. And I don't know why there are all these slides like this. Everything here is intractable. So, okay. This is what we do. Okay? We have X, as I was saying. We go through the encoder, and the encoder finds this Q phi of Z given X. Okay? So we find again our embedding. But we basically force our embedding to be our Gaussian distribution doing this. Our embedding is nothing more than a vector of means and a covariant, and a vector of standard deviations. Okay? So the embedding of this will be two vectors. We use these vectors to sample from the standard distribution containing these means and these standard deviations. Okay? We use this newfound vector as input to the decoder, and then we obtain this distribution, the distribution of p theta given p theta of x given z. Okay? Are you guys understanding? Yes? Okay. So simply our z space, like when we find the embedding is only two vectors. We use these two vectors to define this multidimensional Gaussian distribution. We sample, we reconstruct, and we use our usual L2 distance to backpropagate. Okay? So we can see at this point, as I was saying, that z given x is the Gaussian distribution given the means and standard deviations found from the encoder, and x given z is pretty much the same, right? So let's talk quickly about this math. This is what we want, right? This is the probability distribution that we want to model. So the one of the data, right? So we see from here that this is equal to the expectation over z, and z is taken from, is sampled from q phi of z given xi of log of p theta of xi. Okay? I mean, this is a little mathy. Like, if you guys don't work out all the steps of this, it's still fine. But I find it interesting, but I don't know how much you will use it, especially if you're not mathematicians or trained computer scientists. So, okay. So we can see that the expectation is in respect to z, but we can also see that the probability distribution of xi is not actually dependent on z, right? So if we use Bayes' rule, we reach this, where we have the expectation over z of log of p theta x I given z times p theta of z, which is our Gaussian distribution, right? It's our prior, over p theta of z given xi. Okay? It's just Bayes' rule. You just have to rearrange the terms in it. So if we multiply by basically 1, so by q phi of z over x, so z given xi over the same thing, right? We're not changing really the values inside, but we can at this point rearrange it so that we can use the laws of logarithms to divide this into these three elements, right? These three elements are actually our loss function, like the loss function that we are minimizing when training the variational autoencoder. So we can see. Do you guys know what the KL divergence is? So the only one that answered did this with his hand.
Nobody really knows what it is.
What?
Nobody knows what it is. It's like a measure.
Is that what?
It's a measure between two distributions that are different.
Precisely. It's a measure. It's something that measures the distance. It's a distance between two full probability distributions. Okay. So it is defined as well. Let me pull it up on Wikipedia, which is always awesome. Here, the scale divergence between two probability distributions P and Q is defined. Take the positive one, which is defined like this. Okay. So you can see that whenever the two distributions are the same, right? We always have P of x, which is something between 0 and 1, times the logarithm of something over the same thing, which is 1. And the logarithm of 1 is always 0. And so it means that the two distributions perfectly match, right? Do you have any question about the KL divergence? It's just remember that it's a way to measure how far away two distributions are. Simply this, okay? It's not symmetrical. Yes.
That's why it's not also a metric. So that's why we call it a divergence, not a distance.
Yes, even though this is more often than not used, like everyone. Often, when you use neural networks and you want to match two distributions, you minimize this one because it's more tractable, but it can also lead to undesired effects. In variational autoencoders, it's not a problem per se, but in GANs it becomes a problem. In GANs it can bring to mode collapse and things like these that I will explain next time. Okay? So, okay. So, as I was saying, we have the first term, so that the expectation of the logarithm of p theta of xi given z, and this stays as is, minus, I just showed you what the KL divergence is, right? So you basically have the KL divergence between the function of the encoder, the function of the encoder over the prior, right? Plus the KL divergence of the function of the encoder and the probability enforced by the decoder of z given xi. Okay, this last one is actually non-tractable, but we know that it's always bigger than 0, right? It's either 0 or bigger than 0. If we know this, we can actually just say that we can minimize the lower bound of the distance between these distributions. Okay? So in our variational autoencoders, this would become, these two terms are our loss, and we minimize them to minimize this lower bound. Okay? Does it make sense?
Just to add, since the log of p theta is a constant, so we have a maximization term and the other term, so we go for a minimization of the lower bound, just because log of p theta is just a constant.
Sorry, repeat it again.
So log of p theta is a constant. And we have a task over on the right to the side which basically tries to minimize the KL divergence between the true posterior and the approximate posterior. Since we are trying to minimize that, and we know that the KL divergence is always greater than 0, so the other term would result into minimization. It's just because the expression on the left side, that's log of p theta is a constant.
Okay, yes. Yes, okay, thanks. Any questions? Okay. So, what we do is, what we do is like what I've been talking about for an hour. The first term we enforce, right, using the reconstruction loss of the autoencoders. Okay, so we maximize the probability of the data given Z simply with this L2 distance between the reconstruction and the original data. While the KL divergence between Q and P, we simply basically enforce that the fact that when we find the Z space has to go towards a normal distribution. So we simply penalize the encoder if this doesn't happen. So as I was saying, as I said before, we find this mu and sigma when through the encoder, and in this way we find the appropriate prior. Then we sample from that prior, and we use the reconstruction loss to enforce the first part of the loss. It's really not difficult even to implement. Like, you could go home tonight and implement it in half an hour. If you don't have too many problems with TensorFlow, to be fair. But do you guys have any questions? Okay. Yeah. You train normally, like as you would do any other neural network. Once this is over, you use only the decoder, but you already know that Z is the normal, so you can sample from that. The cool thing about this is that you obtain a generative model whose embedding is still a valid embedding. So the embedding is still useful. The embedding still contains the information that we can use for other purposes rather than just generating, right? But we can also generate it in this case. So as you can see, this was, for example, trained on a NIST. It is the importance of the embedding is shown here in the sense that, for example, you can see. Can you see that it seems, for example, this 6, the first 6, it seems like it's slowly changing from a 6 to a 2, right? Why is this? Because what we can do is sampling from the Z space and then sample again, right? And you can actually interpolate. And the interpolation, every step in the interpolation is still valid, is still a valid input, and it's still a valid it's still a valid input for the decoder, right? Because each of the features that you can find in the latent space, they encode some specific information of the real data. This is not what happens in GANs. In GANs, you still have a prior, right, from which you sample. But if you try to look the distribution of the data in the latent space, it makes no sense. While if you look at the distribution of the data in the context of the variational autoencoders, it makes total sense. Like, you could, for example, find the data divided, for example, for MNIST, each digit could be actually a portion, a separated portion of the space. But this arises naturally. While in GANs, it doesn't. All the latent, like the vectors in the latent space are all entangled. Yes?
So from this picture, am I right that the result of the sampling is not deterministic?
The result of what?
The result of sampling is not deterministic because I can't ask the model, say, I want to generate a 6, but it cannot, well, somehow give you a deterministic example just to randomly generate the result.
Yes, yes. That's almost always with generative models, you sample, but like the basic versions, they don't let you actually say like, okay, I want a 6 or I want a 2. Right? There are other versions of even just variational autoencoders that will let you do this. Right? Because for example, if you just a super thing, probably someone did it. As I told you, I'm not an expert, but I've seen this done in GANs, so I suppose someone did it in this. So, for example, you can have actually one of these dimensions, you can enforce, for example, on MNIST, right? You can enforce the latent space to have this mu, this sigma, and also the classification, right? So if you force it to classify, then when you sample, you can sample from the normal distribution, but then you attach your class at the bottom of the vector and feed it into the decoder. Since it already learned that whatever is like classified as a 6 should actually match the image of a 6, then you know that if you put a 6, you will have a 6. Does it make sense?
Yeah.
Of course, the thing is that to do something like that, you need labels, and this is not unsupervised anymore.
Right.
Right?
Right.
Does it?
So to achieve the goal, could we just only train the image of 6, only train on the image of 6 and let it randomly generate, and then it will be 6, I think.
If you only train on images of 6?
Yeah.
Yeah, but you will not. Okay, but that is the. Okay, you will not obtain the distribution of all the digits then. So, like. Yeah, I mean. Still, you're kind of choosing a different distribution to be able to generate only 6. But like, he was actually asking if it's possible to enforce some kind of. I don't know, how would you call that?
Constraint, supervised.
Yeah, some supervised constraint. Yes, and it is possible. Like there are a lot of papers that do this, especially now, like in GANs. Like it's crazy. It's crazy. So let me show you a few. Okay, this is actually pretty cool. Can you see? This autoencoder was trained on faces, right? But you can actually see that in the vector space, right? In the vector space, there is one dimension that tells how much the person is smiling, and another dimension that determines how much, left or right, the face is turned, right? This is what I was trying to tell you, like the space itself makes sense. The features in the Z space are still features that we as humans can usually make sense of. And this is important because then we can use this for way more than just generating, but also like many other tasks. This latent space still is valid for other tasks. Yes.
What are those tasks?
Classification, mainly. Like a lot of what we do is classification, right? So, but I mean, there are so many tasks, right? Like I don't know, like
the regression or anything like that.
yeah, I mean
Basically, it learns a latent representation.
yeah,
It turns out to be a latent representation learning when you just try to. So there are two terms, as you could see in the loss function of the variational autoencoder. So one term was essentially enforcing that the encoder basically maps to a prior distribution, which is a standard normal, and the other was a reconstruction error. So the reconstruction error is responsible for doing this local clustering, such that, as you could see, that one of the dimension expresses the amount the person is smiling, and the other is the movement of the face. So in this way, you could basically represent or learn the representation of the smile of a person or the face orientation of the person. Let that be cats, dogs, or any number of classes that you have in the input. With this proper functioning of the VAEs, you can get even a good representation of the cats, dogs. By good representation, I mean to say that there will be local clusters that will represent, okay, all these Z values which are close to each other, they will represent cats. The next set of clusters will represent dogs, and like this way. So it basically does representation learning in that case.
does it make sense?
Yes.
So it has got twofold. One is the generative process, and another is the representation.
Any other question? Right. Yeah, we're actually almost done. Like, I'm really not an expert about this. So as I was telling you, like, you see how blurry those faces are, right? Like, they look good. They look like real faces, but they're super blurry. That's why people are kind of moving away from variational autoencoders to generate images, because it's not really a good. The output is never that good, but it's still actually fairly good. So variational autoencoders are still studied a lot, but more for like representation learning right now. So yeah, these are the pros and cons, right? We have a principal approach to generative models, because we are, like, you saw the math that I didn't explain greatly, but you got the gist. So we obtain something that is actually good as a lower dimensional representation. The cons is that we're just maximizing a lower bound, so it's not necessarily the best way to go. And the samples are always blurrier than we would like to have them. Yeah, these are the main things about variational autoencoders. There are many papers that are being published about this, so I would suggest you go on like NIPS or CVPR and take a look. But this is pretty much all. Do you have any questions? Did you guys understand? Like, I am very unhappy about how I explained this lesson today. So, do you guys understand what I was trying to say? Yes. Okay, except for the mathematician there. Anyone else?
I feel like there was just a lot to kind of take in. So I bet you did a good job. It's just a lot.
Thanks. But like, I wasn't actually fishing for compliments. I was really like trying to understand if you guys understood. I know that like, I will explain Gensler like next time. It took me 1.5 years to really understand what those things are. So it's always hard when I have to give you like an hour lesson about this kind of concepts, but at least I hope that you get just the basics to understand. Maybe start on your own if you want, but like this is the main purpose. Yes.
So Burton mentioned that you use this stuff
Could you maybe explain a little bit on how, like, what type of data you use this kind of stuff for, versus like a traditional deep neural net?
What kind of data?
Yeah, I mean, like, if you're having to choose this tool versus something like AlexNet.
Well, this tool is a generative model, right? Like AlexNet, you don't use it for generating. Like you kind of like, I mean, did he say that you use AlexNet to generate?
No. I guess I'm just curious what you're using this on in your research.
Hi. Okay, first of all, like the stuff that we have done up to now is
Discriminative, right?
it's more discriminative and it's more also I mean, we did classification, we did some regression, but like you are not trying in those cases to model a distribution. Do you understand what I mean when I say modeling a distribution? Like modeling a distribution just means understanding, well, when I have data, understanding the process that generated that data. Okay, if I am able to model this, like this distribution, I am also able to generate new data samples that actually look like they were sampled from the real distribution. Okay, so how do you use these? You use them in a lot of ways. Like often, for example, if you don't have enough data, you could try to generate more data through these, right? Like Surajit and I are kind of doing this kind of stuff also for our projects in like the project that fund us. So we are using these generative models for like to generate new data. We're using these also. Now there's a lot of studies on how to generate data that looks like it's from the distribution, but it's not from the distribution. And there is a classifier that will understand that it's not from the distribution, and so it learns better the stuff from the real world. Like there's a lot of these things. If you want to try and make faces, you can actually steal someone's money with the face recognition stuff. But there are people that are actually doing this. Hopefully, they are caught by the police. But yes.
How is there any way to train this by also using something like AlexNet, a discriminative model to help the autoencoding process? Can you see how you can incorporate that somehow to tell the model how to train, like how to treat the Latin dimension properly?
I don't.
Yeah, but in a sense, one could use that for encoding. That's the only purpose one can use it for, just to converge it to the number of classes.
Like the autoencoder, you mean?
No, yeah. So the part of the autoencoder, so the encoding part, one can just employ some network like that for doing the encoding to represent the latent.
Yeah. I mean, but
that's
like
the only thing. But you won't be able to model a distribution with the
Yeah.
BAEs, because in BAEs or at least in
are you
BAEs,
able to hear him?
At least in BAEs, we try to get the parameters of the distribution.
Yeah.
So as a part of, so the basic difference between autoencoder and the BAEs is that autoencoder only generates a latent representation for every data that you feed into the network. Okay. Now considering AlexNet to be one of the possible options that you can use for encoding. So what does AlexNet can do? It can produce suppose you have got 10 different classes, right? So consider the 10 different classes to be the latent variable dimension. Okay, so if Z happens to be 10, and you can employ AlexNet directly to do the encoding part. So that will do a mapping from the pixel space to the latent space.
Yeah, I guess every classifier is an encoder in that sense. But what I was
Yes.
saying is, can you use AlexNet to somehow enforce a prior? I don't know, like put it in the loop. Let's just say
To enforce a different prior.
maybe. I was just thinking you have a autoencoder that goes through. It says, hey, I've generated a giraffe. But AlexNet says, no, that's not a giraffe. And then this makes a gradient update. So it learns that
That's a GAN.
that's not.
That's a GAN.
That's a GAN.
I forget. Sorry, thank you.
So,
Yes.
so am I right that any encoders can have variance of have a Bayesian variance. I mean, we can for any given models encoders we can give the
Like
priors,
enforce this
some
prior?
priors and
Yes.
and make
Yes.
it update.
You can. You have to enforce it though,
Yes.
right? Like the difference is that like he's right. Every classifier has an encoder part.
Right.
It has to, right? The difference is that that encoder that you're finding is specific for the task you're training for, while these ones are good embeddings for many tasks. That is the difference. If you enforce the prior itself, like let's say you want AlexNet to actually encode before the classification to encode to a Gaussian distribution, you can probably do it, but at that point, why would you do it? Just
No, but possibly they can directly employ it. They can't directly employ AlexNet because AlexNet won't provide us the
exactly the
parameters of the
reconstruction.
distribution. So that's what I was
Exactly.
saying. So if you go for the autoencoder, you can directly employ any kind of this discriminative network as a part of the encoding. But if you go for this generative scheme, where you really need to learn the parameters of the distribution, you cannot directly employ these type of generative models. Because when you employ a prior and you want the output of the encoder to match with the parameters of the prior distribution, then you want your network to produce output which are parameters of the distribution, right? So as in this case, you basically try to map the encoder to a standard Gaussian distribution. So the standard Gaussian distribution is 0 mean and a variance of 1. And moreover, it has got entry only in the diagonal. It has got no entries in the non-diagonal elements in the matrix. So as a part of this encoding scheme, you would like to produce two things. One is a mu of dimension d, another is the diagonal elements of the covariance matrix, which is also of dimension d. So you basically, like this way, you try to enforce that my encoding happens to be close to the standard normal distribution. But in case of discriminative model or autoencoder, you directly map the input to a latent space. You don't intend to learn the parameters of the distribution of the latent space. So
what actually is the encoder? What its network? What is architecture? So it is not shown in the slides. And
like what kind of architecture?
So what kind of architecture does the VAE use for the
It can be a fully convolutional, but like if you use images, it can be fully connected, right?
Yes, of course.
But if you use images, you want to use convolutions,
Right.
pretty much. What often happens is that, just a second, huh? What often then happens is that you have like, remember UNet?
Mm-hmm.
So like a convolution, max pooling, convolution, max pooling. More often than not, what I've seen is that kind of architecture.
where you have a bottleneck.
All right.
So like out in the wild, I'm using some type of deep neural net, and I'm not happy with the results of this neural net. Can I then employ this technique to beef up my training data to get better performance on the task?
You could, yes.
And if that's the case, then why isn't it just common to always kind of do some type of beefing up of your generative model before feeding it into a neural?
Sorry, repeat last phrase?
Yes, so why isn't it standard practice to just do this technique before doing a...
Because it's not always, like, if you already start from a small, if you're okay, there are cases in which it is useful. More often than not, if you obtain bad results, you want more the representation part of the autoencoder rather than the generative part of the variational autoencoder, right? Because of what I was saying before, like usually they learn a better representation in the latent space than anything else, more often than not. The problem is also that if you have a distribution, if your data is too small, like the amount of data you have is too small, still the amount of characteristics that you have is still too small, right? So at that point, let me think. At that point, you want to try to maybe find more unlabeled data for your classifier or regressor, and try to find ways to leverage the unlabeled data. Like there's a lot of work on semi-supervised learning. These are more to like, these generative models are more to like, are more for other kind of things, like are used more for other kind of things, either understanding the distribution itself, or yeah, they're using them in a lot of different ways. Like I've been reading a lot of papers, like new papers, that use GANs and variational autoencoders in ways that I would have never thought. But yeah, this is why though, because in any case, the characteristics that they will learn from your data are still the characteristics of your data, and if they are not enough for your classifier, they will still be not enough.
How does the like data size for generative models compare to data size for classifiers? Like, is it generally about the same? Is it more?
Usually, you have huge distributions, but the fact is that the distributions are unlabeled. They are completely like, you can find faces all over the internet, right?
Right.
Like, and it's easy to collect. Right. It's way harder if you have to label them. That's why, like people like GANs and variational autoencoders, because they are completely unsupervised. So just get proceed.
Yeah. I'm just curious why it's called variational. Well, what does the word variational come from? What is that?
From the Bayesian.
Yeah, so
variational inference?
Yep.
Yeah.
Okay.
Where you basically try to approximate the true posterior.
Oh, yeah. I see.
So if you look into the expression of the loss function,
yeah.
you will have a clear divergence between the approximate posterior and the true posterior. So that's why it's very.
So could we take samples that failed or that got misclassified, use those samples to do generative models, feed it back into the network, or at that point were you risking overfitting your model?
I mean, if you train a variational autoencoder on one sample, you're not gonna get a lot out of it, right? Like,
Well, I mean, like every misclassified sample, you do generative model to feed that into.
I don't know. This is a thing you could try. I've never tried that. If you guys don't have other questions, I think I'm done for today. So, thanks.